Hi everyone, my name is Pegah. I'm glad to be here among you. I'm sure you have done some. I'm going to talk about some kind of like modern data science stuff that we are working in football, mostly in the research side of the football, because this is kind of on the research phase yet. Needs a bit more time and trust for the practitioners into the club to go into the real production and so. But these are something that very much top clubs are using these days, not, for example, all other clubs, even in the first divisions. But actually, it gives a lot of ideas about some kind of like a spatial temporal modeling in the which is the nature of the soccer data set. And I hope we have some kind of like soccer fans here now in this meeting. Just feel free to interrupt me if you have any question or if you have any kind of comments on any parts that I'm talking, or if some of the parts are not clear, just let me know. So I'm actually a researcher, football analytics researcher at the Uppsala University. And also I'm kind of like football data scientist and working on some kind of like game intelligences at company to give clubs some kind of like, for example, services such as helping them to gain their optimal playing style, and also what are their opposition analysts, and also scouting methods for different roles such as recruitments or scouting or sporting directors when they want to find the new talents and new players, or scout their own players and so on. Which is kind of, for example, we are helping the video analysts at the club to compare their method to quantify their intuitions and their analysis there. So let's get it started. I'm going to, among all other methods that you will see in the soccer, I'm going to show how, for example, the temporal graph networks and the graph neural networks could help that. But first, I'm giving some kind of like background if you're not familiar with soccer at all. I'm going to talk about some kind of like passing options that we have in the soccer analytics. Then what is the difference between the selection of the player, where to send the ball to or pass the ball to, and also if we will send it to there, it will be successful or unsuccessful. All these stuffs are kind of like very hot and very important in soccer these days. And then I'm going to show you how temporal graph network or graph neural networks could be better in comparison to the convolutional neural networks or even more conventional machine learning methods. And then I'm going to show you some applications that we work on for the offensive passes. I mean, the use cases that we can develop based on the output of these temporal graph networks in order to help to give some kind of like actionable insight to the coaching staffs and also in the player level even. So basically, in the soccer analytics, we have either pass player selection. It means that when we are talking about passing options, we have two components, which is about player selection or space selection. Because soccer is a very fluid game. It's not like basketball or it's not like other kind of team sports that you specifically could send the ball to, for example, hockey. In soccer, the player could send the ball to any kind of any space on the pitch. I'm going to show you now. It doesn't need to go exactly to one teammate player or opponent's player. That's why the modeling approach in passing options are divided into two. The first is actually the player selection, as you can see here. For instance, we have the expected pass model. It means that if the passer is here and the receiver is here, what will be if the player will select to send the ball to the teammate, which is around this flank here, what will be the chance that this pass will be successful? This, as you can see, this could be some kind of like binary classification because we have the label for such a thing, if the pass was successful or unsuccessful, if we know who was the intended receiver and so on. So we can develop some kind of features such as what is the location of the nearest teammates and opponents, what is the location of the ball holder, and what is their speed, velocity, and so on, in order to classify such a thing into goal or into successful pass or unsuccessful pass. So this is one model which is about player selection. It means that the passer selected to send the ball to this player. This is actually our assumption, our modeling approach. And it doesn't need to be exactly expected pass. It could be expected threat. Actually, it means that if we assume that this player selected to send or intended to send the ball to each of these teammates, which are the blue dots here around, what will be the chance that we will have a goal within the predefined time step, within the predefined time window, such as, for example, 10 seconds. We call this like expected threat instead of expected pass. So we are kind of linking it to the long-term goal scoring after the pass was successful. What will be the chance that there will be a shot or a goal within the next 10 seconds or so on? And the next is about the space selection. It means that there are actually a few years ago, about like 3 years ago, I think, the soccer map paper was developed, which was kind of like very pioneer in this work. I'm going to show you. This is based on the CNN. More red shows more actually higher chance of the success, and more blue shows the lower chance of the success. And if we have the ball and this is the, I'm not sure you can see it or not, but here is the ball, the white dot which is here, and the ball holder is here with the ball now. So you can see, for instance, the blue area shows that if you send the ball to each location here, you have the very low chance of getting it a success. It means that it might be turned over by or intercepted by any kind of like opponents around. And the red places show vice versa, successful stuffs. And same here. So this is based on some kind of like a space selection instead of player selection. And the way that we are doing that is based on the convolutional neural networks. As you can see, we are able to convert or make some kind of like image like shape from the soccer field. Here you can see the soccer field is 105 meter in the x-axis, in the touchline basically, and 68 meter whites in the goal line. If we are able actually to convert this or treat the soccer pitch as a image and consider each location of this 1 meter to 1 meter zones on the pitch as a pixels that we might have in this picture. This is not what we are doing for computer vision. I'm just trying to show you how we can treat the numerical data basically into the image, as an image, for instance. This is the numerical data that we are going to get. For instance, we are going to get 11 location from the teammates player, which are the blue dots, 11 location on the opponent's players, which are the red dots. Then we have 11 velocity for the teammates, 11 velocity for the opponents, the distance and angle to goal for each of these teammates and opponents, and so on. And for each of these features that I mentioned to you, which we can call it like a channel, we can make matrices of size 105 to 68, in which if we have location, for instance, for this zone, then the value of this zone will be 1, and the rest of the value that we don't have a player in will be 0. And other stuffs. As you can see, this is kind of like very sparse matrices, and that's the reason we have some kind of like semi-supervision task in this kind of modeling as well. But it might give you some kind of idea that how we are treating the field as a image, and we can develop a convolutional neural networks on that in order to develop some kind of models such as what you can see here. So if the player, if in the previous games or historical games, the player selected to send the ball to any kind of any of the zones that we have in this 105 and 68 grid that we have, if the pass was successful or not. As you can see, this is still some kind of like classification task, but in a very sparse environment, and CNN fortunately is kind of helping, and it was pioneer to help us to quantify the success probability and the selection probability on the full surfaces of the pitch. And these kind of channels are very based on the modeling. We can have as much channels or as much features that we need, and it could help CNN to work. And we need to always balance it with some kind of overfitting and so on. What is the problem now with CNN, with convolutional neural networks? The problem with convolutional neural networks assume that actually it assumes players are a spatial, the players have some kind of a spatial locality. It learns from pixel neighbors and assumes that position relative to the grid matters. This is not the case in football, because actually the player actually, when you are receiving any kind of event data or the tracking data, the player doesn't have to have any ordering. So we should be able to find some kind of ordering ourselves. It means that, for instance, let's say in Manchester City, Rodri and Haaland are not always, for example, player number 1 and player number 2. I'm not talking about any jersey number or something. I'm talking about the ordering of the player in the numerical aspect. So we should be able to kind of find what is the order of the player, and which is not provided in the data. One way to do so, it's an algorithm which is called permutation-invariant sorting scheme, in which we can say that let's consider for this location, for this image, hopefully you can see that, but the ball is here with this blue player. It's a black dots that you can see here. The permutation invariant sorting scheme could help us, for instance, to rank the teammates player according to their distance to the ball holder. So we can set this ball holder as an anchor, and then the distance in the ascending in the ascending order could help us to order this player and use it for any kind of like for any kind of like classification task and ordering task. But the better option is actually to use some kind of matrices, some kind of models that are permutation invariants that I'm going to show you. Basically, in football, first, the problem is that first the player order is arbitrary, the second arbitrary, and the second is that what matters is who is near home, not position in their matrix. As you can see, this is kind of like depends on their relation, not on the exact position on the field. So if we are permuting the order of the player, I'm going to show you in the next slide actually, but let's say we are swapping the player number 3 with 7, or changing Rodri with Haaland. And then CNN see it as a different pattern, which is not actually a different pattern. Just the location of the player has been changed. The player are still have the same identity, and their identity hasn't been changed. But they're actually the spatial configuration is the same, but CNN cannot handle that. Let's just get an idea from here. Pegah? In the CNN, yes.
Sorry, yeah, we have a question. Ingrid, did you have something to?
Yeah, thanks. Quick question. I was wondering, to what extent is the closeness like the primary or the only thing you look at? Because the positioning will matter as well, right? And whether or not there's a player between me and another teammate. Is that sort of a simplification, or is it just the most heaviest parameter?
Totally depends on the channels that that I showed you here, and it depends on our modeling approach. So, for instance, for such a thing, one of the channels are the exact location on each of these pixels that we have. And for the other steps are for, let's say we have another channel, or we have another input matrix, which is about the distance of each of these teammate player and opponent's player to the goal location, which is on the right side.
Oh, okay. So the different channels
Exactly. Different channels have. Exactly.
Yeah.
Another one, for instance, is about the velocity of each of these players. So in total, in this model, we had 11 channels, but it totally depends on the data scientist who is working on that. And let's say feature engineering, something similar to feature engineering and feature selection, that we need to give it to the spatial temporal model.
Thank you so much.
You're welcome.
Yeah. Pegah, sorry, I should have asked you at the start. Do you want to save questions to the end, or is it all right if people raise hands?
I think now is all right. Yeah, sure. You can go on.
Great. Mikhail, you have a question?
Yes, actually, just a quick question. So this analysis, is it sort of momentarily? It looks at the situation as it is now and tries to predict the next move, or does it also sort of take into account longitudinal features? How are players moving? Are they moving up? Are they moving down the pitch?
Yeah.
Just to understand the analysis. And sorry for interrupting.
No, sure. Very nice question. Actually, we have we have some kind of historical data from, let's say, last 2 seasons of the English Premier League. All right. And this is actually could be used as our training data set. We are, of course, separating that historical data into train and test, exactly like any kind of like image classification or whatever we have. And then the task is to test it or predict, use it for prediction, either in real time or for any kind of, for example, new frames that we are going to receive. So when we have such a training model, when we have a CNN that is trained over, let's say, 10,000 previous image or previous data. When I'm saying here, image is total just about the numerical data set. I'm not talking about any image. I mean the numerical data set that we converted into, treated into image. So it could be tested on any kind of new image that we are receiving it here. Let's say we have a CNN that is already trained on the 10,000 previous frames, and it knows that where is based on the task that the CNN is developed on, either on the selection of the, as I show you here, either on the selection of the player. It says that, for instance, what is the next location of the ball based on the previous game. It means that what was the tendency of the player based on the historical game to send the ball to. Or if they have sent the ball to, what was the chance that the pass will be successful or be turned over by the player? In terms of sending the ball to each of these locations on the pitch, this is a multi-class classification task with classes of the 100, with the number of the classes to be 105 multiplied by 68. This is a very big number of the classes as a target variable. But in terms of pass being successful or not, this is a binary classification. So it says that when we are sending the ball to each location on the field, if it will be successful or unsuccessful. Since there are just 2 classes, so we can treat it as a binary classification. And when we have these different CNN models, one for selection and one for success, we can test it or use it for prediction for any kind of new frames, either in real time or in the new frames that we are going to receive. And then when we are feeding this to the CNN, it can, based on the task that the CNN is trained on, it can predict if the pass for what is the next location of the pass for instance, in the next event or in the next time step about next second, or if what is the chance that the pass will be successful if we send it to each of these players on the field. Does it make sense? Did I answer your question, or?
Yeah, thanks.
No, you're welcome.
Cool. Yeah, we have one more question from Ingrid. I just wanted to say, usually we have the Q&A towards the end, but if you want to ask it now, Ingrid, go for it.
Sure, it's all right.
Yeah, sorry, it was quick. So I was just wondering, as a trainer with two seasons, how does or do you have to change the weight of the different channels if you have changes in the team composition?
Team competition, are you talking, for instance, about the first division and second division?
No, if you change players in a team.
Sorry, could you repeat that? I don't think I got it.
If you change players in a team, so the team composition varies over season, do you have to change the channel weights?
Oh, yeah. This is something that we simplified that. I guess we haven't worked onto that yet. We just here we are assuming that the player identities doesn't matter basically. So these are kind of, we are considering them as a very simple dots, and that is the biggest problem of the CNN that I'm going to show you now. And actually that's the motivation of the using graph neural network. That's here it just assumes that there is no difference between the players such as Kevin De Bruyne or Haaland. So it just considers everything as the same. And even if we are training any kind of reinforcement learning or something, it just considers that the player are some kind of agents that have similar tendencies, similar characteristics, similar physical performance and everything, which is one of the biggest limitation of the psychoanalytics and these days. And we are trying to use graph neural networks to sort out such a problem. So just the one limitation basically, that we are considering all players as the same, and we are not considering the changes of the players.
Thank you.
You're welcome. Yeah, as I mentioned, this is kind of like problem about the convolutional neural network. The permutation of the player is very much important, and CNN cannot handle that because it considers that if two players are swapped, then there is totally different pattern, and we don't want such a thing. As you can see here, we want, even for such a structure or organization, when player number here, let's say player number 5 and player number 7 in these zones are swapping, let's say they are swapping. This is not a perfect image, but let's say player number 5 and player number 7 is swapping, then CNN considers a totally different pattern, but we don't want such a thing. When they are swapping, although their location is changed, but their identity is still same. So it's not like, for instance, like what CNN considers is that it just cares too much about this location. When we want to classify the image as a cat or dog, then the feature in these pixels is very much important to according to their exact zone or pixel that we are looking at. But we want to kind of like consider the location, ignore the location and focus on the identity of the player, and make sure that the identities are not changing. When the player number 7 is swapping here, then we still know who is who. That's why GNN here or graph neural networks actually can help. GNN models a player as a node in the graph. Basically, let's say we have each node to be one player, and the location of the player, actually XY location on the field, with the edges capturing the interaction or distances, for instance, the passes or proximity of the player. And it's also very helpful for the permutation invariant stuffs, which is a very big deal in most of the data set, and specifically in the soccer. The model cares about the relation, not about the input ordering, and it's also good for the better relational reasoning. It means that we can focus on who is connected to whom and how strongly they are connected to each other, instead of focusing on the pixel that they are located into in a very static manner. So if you want to just summarize, GNN could help for understanding the player identity. As I mentioned, as I'm trying to mention it several times during my different talks these days, is that player identity is really much important. in the analyzing the soccer data, which is unfortunately very, very much ignored these days in soccer analytics, and they are considering different expected goal or expected model for the different players, such as Kevin De Bruyne, and also like Rodri or other people that other players that we have. And all the problem with such a thing is that since machine learning considers everything as all the players same or with similar characteristic, or as agents that, or that's as a physical agent that they don't have any physical performance or something like that, then could be the reason that the scouts or the practitioners, people at the clubs do not trust machine learning models, so on. But here we have the GNN that hopefully is going to help us to consider the player identity and consider some kind of like player characteristics, such as their statistics and their physical performance in the previous games, such as what is their historical expected goal and what is their distance covered during the previous game. Does the fatigue related data help affects him or her on dropping the success rate, or for instance, when if he's running more, will he be more tired or no, and what are the other tendencies and so on. Considering their ID, I have kind of like difficulties these days, since the only way to consider the ID as a node feature in the graph models is to use one-hot encoding, which is kind of like impossible, since we have at least, let's say, when we are training on a data, we have at least 500 players. And working on 500 one-hot encoding of the IDs is kind of like nightmare. It's impossible. If any of you guys have any kind of like a solution, a suggestion or something to include these IDs, please do not hesitate to contact me. But on the other hand, other kind of statistics of the player could be simply added as a node feature for each player identity. And then we can go on with some kind of like player-specific expected pass metrics or expected threat metrics that we can develop on player level. Then graph neural network could help for context-aware behavior, such as model through message passing and the neighbors. As you can see, we are not treating them as pixels inside the picture anymore. Instead, with some message passing options that you can see in the bottom, we can help to aggregate or embed some kind of like features on the node level. So the player will know that who is the ball holder will know that who is the next opponent, who is the nearest opponent, who is the nearest teammate, which the teammate has the highest chance of the pass to be successful, and which player is the optimal direction of the pass to send the ball to. Then we have some player-specific metrics with as an output of the GNN, so we can have some node-level prediction after final CNN layer. As I mentioned, and one of you asked, for instance, we can have either the pass selection probability. It means that who is the most probable next receiver, or what is the probability that if that guy is the receiver, then what is if the guy is the intended receiver, what is the probability that the pass will be really successful, not to be turned over by the opponents. I'm just trying to say that we can have different tasks for the graph neural network according to the output, the final layer of the GNN. And then also another advantage of the GNN is flexibility over time, because we can use some temporal aspect of the GNN, which is a few years ago, temporal graph networks is introduced, which is very interesting, and I'm going to show you. It helps for the sequence learning. So the player will remember what has been happened from the beginning of the possession, let's say. What was the previous action? Was it a pass, or was it a dribble, carry, or whatever that we have? Here is the temporal graph network, or TGN in short. It's very, I'm kind of like a very big fan of that. it helps very well in terms of like soccer modeling, player modeling, and spatial configuration and the pitch. There are several reasons. It can handle the permutation-invariant characteristic of the data. It can handle the temporal characteristic of the data. Consider that we have player number 1 in time step T1 passes the ball to player number 2. Then player number 2 in time step T2 passes the ball to player number 3. Here, as you can see, we can have T1 and T2, but with any kind of other graph neural network which are not temporal, we cannot model this kind of time steps. What was the time between two actions and so on. Then temporal graph neural networks could help us to create some kind of like memory or messages, let's say, for each of the time steps that we are receiving. Let's say, for instance, there is a message from player number 1 in time step T1. Then there is also a message for player number 2 in time step T2. And then the rest of it. As you can see here, we have 2 messages for player number 2, one in time step T1 and in time step T2. That's why we need some kind of like aggregation function. Let's say just mean. It doesn't need to be average or something. It could be any kind of like this could be solved with ablation studies, but we can try with different kind of like aggregation metrics. And then, as you can see here, we can have the messages or some kind of like memories for each of the player that you can see here, player number 1, 2, 3 at each time step. And with this, then we can create some kind of node embedding for the TGN. And then the final layer, as I mentioned to you, according to the activation function that we are setting at the final layer of the graph neural network, we can help it for, we can train it for some kind of like age prediction, which is about if the pass will be successful or not. Let me show you actually here one of the modeling, that's one of the modeling of the final layer. Let's say here there are some kind of like players that they are passing the ball to each other, teammate player basically. Player number 1 in time step T1 sends the ball to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 2, 2 to 4, and then we wanted to know what will happen at the time step T7. The player number 4 will be interacted with which player available on the pitch. And this is kind of like edge link prediction or edge prediction task in the soccer in the world of the graph modeling. Then let's say if the here in the table in the right side, you can see here we have offensive player OP as a sender, basically as the current node, which is in this node 4. We can have it like opponent's player, offensive player or defensive player. B is the ball, T is a touchline, and G is a goal. So if there is interaction between the offensive player and offensive player, it means that if both the sender and the receiver are offensive players, then this is a successful pass basically. But if the sender is the offensive player and receiver, based on the edge prediction or link prediction, will be the defensive player, then we can model such a thing as a tackle. Then this is totally, it was our idea of the modeling. Anyone could go with any kind of other modeling task based on, first of all, based on the considering that what are the identity of the nodes, and also based on the what kind of nodes to include. For instance, I just decided to include touchline, goal line, and ball as a nodes as well. But if you see other kind of papers, they are considering only the teammates player as a nodes. And then, for instance, if there is a interaction between the offensive player with the goal, then this we can model it as a shot, and the rest of the thing that you can see here. And if there is interaction between the ball and the goal, then this is a goal, kind of successful shot, basically. If you want, I just want to give some idea about the node feature and edge feature that we are using. Nodes basically here could be attacking player, defensive player, and goal lines, and also the ball. Totally, as I mentioned, is totally depend on the modeling. Most of the other papers only consider attacking player as the nodes. And then some features, node features or dynamic node features could be location of the player, X1 location on the field, velocities, distance and angle of each node to goal, distance to the ball carrier, and so on. And the edges basically could be the passes or any kind of other actions that you can see here. And the feature of the edge could be a flag defining the relationship between two nodes, if they're teammates or players, or teammates or opponents or whatever, and the distance between the two nodes, how far these two nodes are from each other. This was about the temporal graph neural networks. I am kind of really fan of this because training it is kind of easy, and there are some kind of ready packages for that. By the way, temporal graph neural network is not it has a ready package. It's not our contribution. It's you can check it online, but there are everything. There are some kind of ready packages that you can use to train your any kind of like sequence modeling on it. It's very helpful, and I really recommend it to whoever who wants to work on some kind of like permutation invariance and also the temporal aspects of the data. And then I'm going to very quickly show this one application, not application, actually use case that we can work on. That makes this kind of analysis interesting for the coaching staffs and the people at the different clubs. It could be based on here, let's say when a player is facing a defensive structure, which is a convex hull from the opponent's player in front of him. The red dots are the opponent's player and the blue dots are the teammates. This guy is here the ball holder, and he's facing this defensive structure here from this polygon. And then there are some kind of defensive lines as well, which has been created based on the clustering, K-means clustering of the opponent's location in different areas. All of this has different setups. I'm just very quickly showing it to you, just to give some kind of ideas. These black lines are the defensive lines, and here this dotted polygon is a convex hull that we are using as a defensive structure basically. So when we have this defensive line, this is totally dynamic. For each frame that we have in the data, such a structure varies, and we should be able to have automatic code to generate this defensive line and defensive structure per new frame that we are receiving it. And then one application of the graph that I showed you, it could model it. Then we are modeling it as a different options that this player has. If he wants to send the ball to this player, then this is a line breaking option because it has just break the line. But if he wants to send the ball into such a defensive structure and to be received by a teammate player inside this defensive structure, then such a thing could be called like penetrative pass. Totally, again, our naming. It could be have any kind of other names. And if the ball just passes through this defensive structure and to be received by a player out of this defensive structure, then such a pass is called like through ball. Again, based on our naming and our modeling. Then the graph neural network could help this player to rank these passes and to decide which option is more based on the stuff that I showed you, the node features, edge features, and the training task. We can the task that we train the GNN or TGN on to predict each of these. For instance, we can train the TGN to predict if we send the ball to this guy, what will be the chance that there will be a shot within the next 10 seconds. So it can consider the threats of the sending the ball or expected threat of sending the ball to this guy. Or another thing could be, again, expected pass. What is the risk of sending the ball to this guy? What will be the chance that the ball will be, if he is intended, what will be the chance that he successfully received that? or to be intercepted by one of these two opponents that they are here. All of this could be modeled basically. And then based on that, these are some applications that we can, or not application, I keep saying application, let's say use cases that helps the club to very overall see what are the availability of the strikers, attacking midfielders and wingers based on the different pass type. Pass type 1 is the line breaking, 2 is the penetrative pass, and 3 is the through ball. And here, for instance, we can see that attacking midfielder are the most available player for the line breaking passes. And when it comes to the penetrative passes, the strikers are the most available players. And what is the score generation analysis? Basically, we can analyze that what is the chance that there will be a goal after sending the ball to, after choosing each of these passing options. And here you can see for the strikers, trying pass type 3, which is the through ball, could generate more score because they are kind of like more tend to the right. And then actually for most of them, through ball could generate, which is this green KD, kernel density estimation. The green can create more scoring options, but there are more variances on this. For instance, look at the midfielders. The variance of select resulting to a goal is very high for the attempting pass type 3, but pass type 1 has a low variance, so it's kind of more focused on one specific. It doesn't have much scoring probability, but it seems like at least it's not very much distributed or variated through the data. And the final thing that I want to show you is kind of we can model such a thing, such a reinforcement learning. And this is a problem that one of you mentioned, that still maybe we are not very much ready for such a thing. Although I introduced that, but it might not be very much practical these days, since we cannot consider the player as just agents, which is not true. We should have some kind of like limitation on their physical performance and the rest of the software each player. But just give you an idea, we can model it as a Markov decision process. And here we have some kind of like interaction between the different player inside the possession. And then we can use the Bellman equation in order to use the short-term rewards from each of the atoms that we can see here through the possession, and then use the Bellman equation to aggregate it, and then use this as an objective function and maximize it. So we can see that we have now the short-term reward, but what will be the optimal action that could have been done in order to, for instance, now the actual action here is long ball from here to here, but and there are some kind of like R2, which is the reward number 2 assigned to that. But what could have been that optimal action that could have maximized such a modeling or such a action to maximize the expected goal or expected possession outcome at the end of the possession, and so on. And it could, the reinforcement learning could help us to understand what is the optimal direction of the pass. Let's say for this situation now, the current action of the player, it means that the actual action of the player was shooting it to the goal, but it didn't result to the goal because the player basically made a mistake. It had very low chances of scoring, but the reinforcement learning highlighted that it should have been sent the ball, pass the ball to another striker, teammate striker, and this guy could have had a very high chance or high expected goal for such a location, because his location was better, his angle was better. And then the player basically missed his chances of a score. The team missed this chance because of the bad decision of this player. And the reinforcement learning here highlights the difference between the actual action and the optimal action. And here is exactly the moment that the player is just sending the ball to this guy, and this midfielder just starts to pass instead of sending it to a striker teammate. I'm talking about this moment exactly, this guy. So this guy had the maximum chance of scoring to the goal, but his teammate didn't pass it through. And then the team basically missed this chance because of the bad decision at this time second of 20 of this player who was kind of like selfish and chose a bad decision at this moment. He should have sent the ball to the striker that had very good positioning, and the reinforcement learning could highlight such a thing. And then based on that, we can provide some kind of analysis for the clubs that you should have increased the tendency of the backward or forward passes and the rest of the thing that you can see here. And finally, we can use it for the in-game outcome prediction or some kind of like bet modeling or gambling. This is could be also academic as well. And when we have some kind of difference between the data points in terms of being optimal or not, then it could help us very, very, very well in terms of predicting who will be the winner at each moment of the game. The current application of such a thing is now for the club. We are not selling it to any kind of betting companies, but we will see later. Then in the real time, basically the analyst could see that who has the highest chance of win, who has at each time step from 0 to 90 minutes, which team has the higher chance to be scoring and to win the game, basically based on the features that you can see here. And yeah, I think we can stop here. I would be happy to answer if you have any question or something. I hope you liked it. But this is what we are working on in a sports analytics, and we are helping clubs to make some kind of more informed decision based on these advanced models.